Hi, everybody. In this lesson, we're going to look at geometric series. So geometric, we already know, is repeated multiplication. We already know geometric is repeated multiplication. And instead of looking at sequences, we're going to look at a series. And a series is a sum of a sequence. So I'm going to take the list of my numbers, and instead of just having that list of numbers, I'm going to add those numbers up. And geometric series are really essential for later mathematical concepts that we do later, really in Calc 2s the next time they pop up. So for those of you continuing on your math journey after high school, taking Calc 1 and Calc 2, in Calc 2, geometric series make a huge reappearance and are actually very important for a lot of calculus concepts. They also have a lot of real-life applications that we're going to look at in the second and the last third of this unit. So to get us started, use this sigma notation, write out the following sum, and find its values. So I'm going to walk you through this one because it's been a while since you've seen sigma notation probably. So we start down here. I start by plugging in n equals 1. So the first thing I'm going to do is plug in n equals 1. And this big sigma means find the sum. So now I'm going to plug in, I did 1, now let's plug in 2. And I keep going, I keep plugging in until I plug in that number on top of that Greek letter sigma there. So I keep adding, I just keep adding, I plugged in a 7, so I'm going to stop. So at this point now, type all that into your calculator while I walk across the room to go get my TI-84. I'm back with my calculator now. So I'm just going to type this all in. 5 times 2 to the 0 plus 5 times 2 to the 1. Because I'm doing 1 less than that exponent says I should. So I'm typing this in, 2 to the 3rd, 2 to the 4th, 2 to the 5th. And the last one I really plug in is 2 to the 6th there, because 7 minus 1 is 6. So for this sum, I got 635. If I add all of these numbers up, I get 635. Well, what numbers am I working with? Well, this is an explicit formula for a geometric sequence. This is an explicit geometric sequence. Start at 5, and the common ratio is 2. So 5, 10, not 15, I'm multiplying by 2. 5, 10, 20, 40, 80, 160, 320, 1, 2, 3, 4, 5, 6, 7. Those are the 7 terms that I'm adding up. I'm adding 5 plus 10 plus 20 plus 40 plus 80 plus 160 plus 320. And when I added that up, guess what I got? I got 635 again. So this is a geometric series that I'm working with because I'm taking this sequence and I'm adding all the numbers up. And to start this lesson, we're going to come up with a formula that we're going to use. We're going to come up with a formula so we don't have to do all of this. We're going to plug in a couple things to the formula, and it's going to spit out the sum, which is the nice part of these geometric series. So I'm going to derive this formula for you. You can skip ahead to the end of this and get the punchline, but I'm going to show you where this formula came from. It didn't fall from the sky. So let A, AR squared, AR cubed, and so on be a geometric sequence with a first term of A and a common ratio of R, say like a pirate, R. So we have A times R, A times R times R, and I keep multiplying by R. So the sum of the first n terms, the sum of the first n terms is what that S means. The sum of the first n terms is given by this sigma notation. Here's my explicit formula. I'm indexing I from 1 all the way up until n. And this is what I'm getting. I'm finding this sum here, AR squared, all the way up to AR to the n minus 1, and I'm adding those all together. So what I'm going to have you do is find R times that sum. So I want to know what is R times the sum there. So let's do R times that sum, A plus AR squared plus dot 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 plus AR to the n minus 1. So let's apply the distributive property and see what we get here. We get AR squared, repeated multiplication becomes an exponent. And then I do a lot of distributing in that dot 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 there. And look what I'm going to write one more term here. So what comes before this? What's the first term in this dot, dot, dot here? Well, AR to the n minus 2. So that becomes n minus 1 when I add another r, multiplied by another factor of r. And this last term becomes what? AR, I add the exponents. N minus 1 plus 1 gives me to the n, because I stuck on another r to that term. So that's r times my sum. So now what we're going to do now is beautiful things happen here. I'm going to find my sum. So Sn minus that thing I just created. Well, what does that give me? Sn is my original sum. I'll write IR cubed. I added an extra one there. AR to the n minus 1. I'm doing that minus all of this good stuff that I just created above. AR squared, AR cubed, plus dot, 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 plus AR to the n minus 1, plus AR to the n. So I'm finding that difference there. And watch what happens if I distribute that negative through. I've got AR and negative AR. Goodbye, goodbye. Oh, you guys missed that, didn't you? We have AR squared and negative AR squared. Goodbye, goodbye. I've got AR cubed and a negative AR cubed. Goodbye, goodbye. I've got a dot, dot, dot minus a dot. Goodbye, 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 goodbye. And what does that leave us with? Well, that term drops out because I have a positive version and a negative version. So all that collapsed. That sum, this difference here, it collapsed so that all that I'm left with is a minus, all of this dropped out, minus AR to the n. So here's the punchline for those of you who skipped ahead. This is where you should join us again. I have the sum minus the common ratio times the sum equals A minus AR to the n. And I want to know what's the sum. So I'm going to factor that Sn out, and I'm left with 1 minus r. And I can finally get that sum by itself. The sum of the first n terms of a geometric series is the first term minus the first term r to the n over 1 minus r. That's the punchline for those of you who skipped ahead. To find a geometric series, I need three things. I need the first term. I need the common ratio. And then I need how many terms am I adding up? How many terms? Once I get those three values, A, R, and N, we plug it into this little fraction here, and it spits out the sum. So that's the formula that if we were to take a Regents exam, and I still don't know if we are yet, that's given to us on the reference sheet. So I will always give that to you, or you can always flip back in your book, since I'm not giving you anything right now virtually. You can flip back in your notes and realize this is the formula. So the formula, the sum of the first n terms is A minus AR to the n. Sometimes I put a little subscript of 1 there. A1 minus A1R to the n, 1 minus R. So use the formula for the sum of a geometric series to find the value of the series from the opening exercise. So the opening exercise here, I need the first term, the common ratio, and how many terms? Well, the first term is 5. The common ratio is 2, and there's 7 terms. So instead of doing all that work, I could say the first term is 5, the common ratio is 2, and there are 7 things I'm adding together. So the sum of the first 7 terms, S7, is 5 minus 5 times 2 to the 7 all over 1 minus 2. And all I have to do now is type that into my calculator, and that's going to spit out the answer. Use the fraction button, alpha, y equals, enter. That makes you the fraction. You want to use the fraction button here, otherwise you're going to make mistakes. And all of you have access to a TI-84. You can use that link I posted a while back from Texas Instrument that gives you the software, or if you're on a Chromebook, gives you the emulator on that Chromebook. So make sure you're using alpha y equals enter. Make sure you're using that fraction button. And what a surprise, we got 635. We got 635 as that sum. So instead of doing all that work, I can plug into this formula here and we're done. So let's practice. For each of the following geometric series, find the sum. All right, so I need three things. I need a first term. My first term here is 3. What's my ratio, my common ratio? What's my multiplier? What do I keep multiplying by in this series here? Well, to get to the next term, I keep doubling it. How many things am I adding up? 1, 2, 3, 4, 5, 6, 7. 7 things. So the sum equals a1 minus a1r to the n over 1 minus r. That's all I have to do. Now I know you're sitting there saying, Coach, I could have just added all those numbers up in my calculator. Very true, but what if I didn't give you all those numbers? What if I said find the sum of the first 730 terms? You're not going to sit there and add 730 numbers up. You're going to let your calculator do the work. I got 381, and just for fun, I will type all the numbers into my calculator at once, just as it's written on the paper, like any second grader would add these numbers up, and I also got 381. That's it. That's how we use this formula. You plug in these three things, and it spits out the sum. So let's slide over here. First term, 1. My common ratio is 3. How many things am I adding up? 1, 2, 3. Oh, comes next in line. 27, 81. 81 times 3 is 243. Times 3 is 729, and then times 3 brings me to there. So I'm adding up 1, 2, 3, 4, 5, 6, 7, 8 things. I'm adding up 8 things there in this geometric series. So the sum of this geometric series is a1 minus a1r to the n over 1 minus r. And all I'm doing now is typing that into my calculator, and that adds everything up for me. Series are all about repeated, it's not repeated anything. It's all about adding up whatever the sequence is. So I get 300, so 3,280 is the sum. Let's look at this one here. So hopefully you recognize this is an explicit formula for a geometric sequence. A1 r to the n minus 1. So my first term is 5, right? When I plug in a 1, I get 5. My common ratio is right here of negative 1/2. And how many terms am I adding up? Well, let's see. Start at 1, 2, 3, all the way up to 10. Now, here's where you don't want to add up all these numbers because they're crazy decimals, and you're not going to have the mental capacity to sit there adding up all those crazy decimals. So let the formula do the work. The sum equals the first term minus the first term times the common ratio to the n over 1 minus the common ratio. Careful with your negatives there. So 5 minus 5 parentheses negative 0.5 to the 10 over 1 minus negative 0.5. I got 3.33, and it keeps going on forever, but I'll stop right there. I got 3.33, actually I'll go out a little bit more, 0.078,125. That's what I got for the sum of this geometric series here. And one more like this, 40 times 1.005, 40 times 1.005 squared. What comes next in line? 40 times 1.005 cubed. So it looks like my first term here is 40. My first term is, what color haven't I used yet? I haven't used green on these problems. That's not green, that's red. A1 equals 40. You're all going, use the galaxy pen. A1 is 40. The common ratio is 1.005. Right? Each time I keep multiplying by another 1.005. And how many terms do I have? You got to be careful here. You want to say 11, but there's not 11. That has an exponent of 1, that has an exponent of 2. There's 11 of these guys, but then you also have that first term, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's also that plain old 40, so there's really 12 terms you're adding up here. That's where you have to be careful with this one. So the sum equals 40 minus 40 times the common ratio to the n over 1 minus the common ratio. And this problem probably comes from some kind of money formula, so I'm going to round it to 2 decimal places, just because this I'm modeling this problem after stuff we're going to look at in the future, where we deal with compounding interest and all that stuff that you thought disappeared, but didn't actually disappear. 493.42. That's how much money I would have if this geometric series existed. So hopefully you feel comfortable plugging into that formula. We got a couple more problems where we're going to play around with it, and then we'll do an application problem, and then that's the lesson for the whole week. So the sum of a geometric series with 4 terms is 60. So n is 4, and they're telling me the sum is 60. So this is just kind of a little algebra problem with the formula. The common ratio is 1/2. So I have everything but the first term. So let's plug it into the formula and just do a little bit of algebra here. The sum equals the first term minus the first term times the common ratio to the n all over 1 minus the common ratio. So I have to end up solving this equation here. So a lot of the times we're going to be encountering things that look like this. So what's really on the bottom there? That's really 60 parentheses a1 minus a1 times 1/16. 1/2 to the 4th is 1/16 over 1/2. So to get rid of a denominator, I'm going to multiply both sides by 1/2. So 30 equals a1 minus a1 times 1/16. And then you can combine like terms there, but I think it'll be easier if you factor out a1 there. So 30 divided by 1 minus 1/16 is a1. That's my first term here. 30 divided by 1 minus 1/16. And a1 comes out to be 32 when you type that into your calculator correctly. So the first term of this sequence is 32, and the sum of the first 4 terms would be 60. So it's just doing a little bit of algebra with that formula. We're going to be doing a little bit of this in the future, so I need you to feel comfortable with this process here of how to get that first term by itself. A geometric series whose first term is 3. All right, geometric series. I know the formula I'm going to use. A1 r to the n over 1 minus r. There's a loud bird outside right now. The first term is 3. The common ratio is 4, and the sum is 4,095. Determine and state the number of terms. So we're solving for n here. So the sum, 495, is 3 minus 3r to the n all over 1 minus r. So what's really in the denominator there? 1 minus that is -3. So I'm going to multiply that -3 up. So 4,095 times -3 is -12,285 is 3 minus 3 times 4 to the n. Now I know it's tempting, but you can't multiply that 3 and that 4 because that 4 has that exponent. So let's move over to 3. So I'm going to subtract 3 from both sides. And you get -12,288 equals -3 times 4 to the n. And hopefully at this point you've said, but my variable, it's so high up there. How can I bring it down? Hopefully at this point you've said that. 4,096 equals 4 to the n. But my variable, it's so high up there, well, I'm going to use a logarithm. I'm going to use log base 4. Logs equal exponents of 496. So we're going to use logarithms here. You could have logged both sides for my 6th period crew. I know I taught that a little bit differently to you guys. Log base 4 of 496 gives me my exponent of 6. Okay, so logarithms are fair game because we might be solving for that unknown exponent. So know that that's an option. Let's do a word problem and we'll call it a day. So Deshaun is in his 5th year of employment as a patrol officer for the Metro Police. His salary for the first year of employment, so my first year, my initial amount, A1 is 47000. Each year after that, his salary increases by 4%. So I'm growing by a percentage, which tells me I'm geometric. I keep multiplying by 1.04. That's my common ratio. What is the sum of Deshaun's salaries for the first 5 years of service? So notice, I don't care how much money he made the 5th year. I want the sum of all 5 years, year 1, 2, 3, 4, 5. I want those all added up. So this is a geometric series. 47000 minus 47000 R to the n, 5 years of service I'm counting here, over 1 minus R. All we have to do is type that in. That's all we have to do to see how much money Deshaun made together for his first 5 years of service. Not the 5th year. I'm finding all of the years together. So that sum, how much money did he have? $254,567 and 16 cents. Deshaun definitely earned those 16 cents. So hopefully you realize the difference between a sequence, what's the 5th term, and the geometric series here, which is find the sum of those first 5 terms and add them all up. So if Deshaun continues his employment at this rate of yearly salary, which year will the sum first exceed $1 million? So the sum equals $1 million. The first term is still 47,000. The common ratio is still 1.04. We're solving for n. So 1 million. 1 million equals A1 minus A1R, say it like a pirate, to the n. Oh no, but my variable, it's so high up there. I'm going to subtract those numbers on the bottom there just to make my life a little bit easier. Negative 0.04. And I don't have a lot of space. We're not going to do this last question here, so if you need more space, feel free to write into it. First step, I think, is to multiply by negative 0.04 on both sides. So 1 million times negative 0.04 gives me negative 40,000 equals 47 minus 47, 1.04 to the n. I have to get that n by itself, so let's move over this constant term here. So negative 87000 is negative 47000, 1.04 to the n. We're getting closer. I have to divide that coefficient away now. I can do mental math here because I'm in 11th grade. 87 over 47 is not going to be a nice number to the n. So now that I'm at this point, I can rewrite it as a logarithm. Log base 1.04, logs equal exponents, so what's left over is the 87/47. So I'm typing into my calculator here, log base 1.04 of 87 over 47, and I get 15.7. So about 16 years, I'd say. The 16th year, Deshaun will have made over $1 million in total. He's not making $1 million his 16th year. The sum of all of his years added up, growing by that 1.4, that 4% increase will give me $1 million. So hopefully you feel good with this formula. We're going to practice it this week, and I'll see you next week. Enjoy this light week, guys. Use this time to catch up. Use this time to catch up in my class and in your other classes. See you guys soon.